So, good afternoon, everybody. In the last lecture, we had discussed particularly the property of the heat kernel. Firstly, I told you how to develop the heat kernel for the corresponding problem, and then we have seen the various properties of the heat kernel, particularly in the context of good kernel, and then what are the advantages of having a properties of the good kernel. So that way we have seen the various problems in the bounded and unbounded domain, and for one-dimensional case, and later on we shifted to the multi-dimensional problems. Now in this lecture, here I will start with the non-homogeneous problem. So here I have included one non-homogeneous problem. Then of course it's a uniqueness theorem, and as I discussed the integral transform technique, particularly Fourier transform for the solution of heat conduction equation with respect to x variable. So few students in the last lecture asked me about the Laplace application of the Laplace transform. So I have included one problem of the Laplace transform, and then we will discuss some recent developments. So here it is the first problem, non-homogeneous heat conduction. Non-homogeneous in the sense this is the heat conduction within an infinite rod with heat source. As I told you the development, derivation of the heat conduction equation. So in the heat conduction equation, this particular term represents internal heat generation. So this is the internal heat generation, and whenever internal heat generation is there, otherwise earlier it was 0, right? So with the initial condition, for simplicity purpose, firstly I have taken 0 initial condition, and later on we'll just discuss about the non-zero initial condition. So this is the problem, this is the heat conduction problem in the infinite rod with internal heat generation and subjected to 0 initial condition, and we are interested to find out its solution. So for that purpose, what I will do, I will design a parallel problem. Parallel in the sense here, V is a function of x and t, earlier was also a function of x and t. Here I will define this particular problem in the neighborhood of tau, or otherwise you can say t tends to tau. Okay, so how this problem is designed? This problem is designed, I have converted the non-homogeneous problem into homogeneous one. I have not taken any internal heat generation case there, and this internal heat generation term I have taken it as a initial temperature prescribed on that infinite rod. So this is how one can develop a parallel problem. Once again, let me explain. In our original problem, the infinite rod is under consideration. The temperature is function of position x and time t, and one more important characteristics I have added today, that is nothing but internal heat source, and heat source was a function f, which is again a function of position x and time t. But as this is a problem, non-homogeneous problem, in order to find its solution directly also we can find by using the integral transform technique. But here I will show you another simple technique how can we solve this problem. So in order to find this solution, what I will do, I will design a parallel problem of homogeneous heat conduction within the infinite rod, and homogeneous means this internal heat source is taken it as a 0, whereas that internal heat source term is considered as the initial temperature. Whenever T is equals to tau, this temperature is prescribed. So this is the way we have designed a parallel problem. And now I can write the directly solution of this problem. Why? How can I write the solution of this particular problem? Because if you remember properly, I have already shown this particular problem. Slides are not moving again. if you remember this problem we have discussed in the last lecture, and this is very parallel to the last one. I will go back again, but let me explain what problem we have considered. So this is one dimensional problem without heat generation in the infinite rod. No, just go back. Okay. So this problem, and we solve this problem with the help of Fourier transform. You can see here, this is a without internal heat generation problem where initial temperature is non-zero initial temperature, some arbitrary function of x, and f is bounded and continuous, and of course in the order to have this boundedness u and ux, it tends to 0 whenever mod x, x tends to minus infinity or plus infinity. This problem already we have solved, and the solution of the problem with the help of Fourier transform was like this. Now the problem under consideration is also similar to this one. Only thing is that we are discussing the problem in the neighborhood of tau, and therefore in this particular solution the t is replaced by t minus tau. That is only the change, otherwise everything is very same. That's why I will not go well in detail. Okay, you just go back. Back. Okay. So here it is now this problem, and what type of problem just now I have shown, exactly same problem. Only this problem is under consideration within the neighborhood of tau, and therefore what I did in that particular solution, I have changed initial temperature is now this. No. Just go back. Okay. So this initial temperature, which is a function of x and tau, here x is after converting to the Fourier transform and its corresponding parameters, it will be xi of course, and t is replaced by t minus tau. That is only the change. Everything is exactly same. If you want to do, you can solve this problem later on as an exercise. Okay, but with the help of that earlier problem solution, I have written directly. No, just don't move this slide rather. Back. Okay, so here it is. I have written solution of this parallel problem first of all, and parallel problem solution is written with the help of that earlier problem whatever we have been discussed. Now this is already I told you. Now the solution of the original problem, which is defined in the equation 67 and 68, is given by uxt is equals to integral 0 to t v of xt tau. Why I can claim this is the solution of the original problem? Because the parallel problem whatever we have been designed, this is designed in the neighborhood of tau. Okay, and now tau, of course, if I integrate the solution of v within the complete range of time variable 0 to t, then of course this will give me a complete solution of the original non-homogeneous problem. And I will of course verify how this particular integral equation represent the solution of this particular problem. So verification is also I have been included over here. So how can we verify whether this particular integral equation given in the equation number 72 represent the solution of the non-homogeneous problem? So what I will do, I will calculate the term of ut, I will calculate uxx, derivative with respect to t, derivative with respect to xx. I will substitute, I will put these values in the governing differential equation, and I will show that this particular integral equation satisfies the governing differential equation number 1. But as we are aware that the governing differential equation is not good enough, we will have to check whether this particular integral equation satisfies the initial condition or not. So that is also, we will check whether it satisfies the initial condition or not. So I will check, I will substitute this particular value in the governing differential equation as well as the initial condition, and accordingly I will check whether this particular integral equation satisfies the given boundary value problem or not. If it is satisfied, then of course this will be the closed form solution of the given problem. So for that purpose, what I need to do, I will have to differentiate this integral equation with respect to t. Now the question arises, now limit is in terms of t, inside function is also of v is a function of t, limit is also in terms of t. Then how can we differentiate this particular integral equation, particularly in the case that where limit is itself is in terms of t. You got my point? You might be aware that the differentiation under integral sign, okay? Otherwise, I have mentioned what is that rule of differentiation under integral sign. If suppose the integral equation is there of integration of a of x, b of x, means the limits are function of x, I mean to say, f of xt, and if you want to differentiate with respect to x, okay, then how can we differentiate this particular integral equation? So way of differentiation is like this. This is known as the Leibniz rule of differentiation under integral sign, and rule is like this. Firstly, you'll have to shift this derivative inside the integral, and what your integrand function is there. I mean, you'll have to take the derivative, of course, partial derivative, multiple, because of multiple variable. You'll have to take a partial derivative of the given function with respect to x, and then integrate within the prescribed limit. This is number one term. Number two term, what you will have to do, you will have to replace this t by, because limit is with integration is with respect to t. Therefore, replace this t variable by the upper limit. Upper limit is b of x. Therefore, t is replaced by b of x, and derivative of b of x with respect to x minus, again same function f of x, and replace t by lower limit ax. Okay, replace t by lower limit ax and derivative of x with respect to x again. So this is the way that we can differentiate the integral equation, particularly in the case that where the limit is in terms of that particular variable. So here you can notice that limit is in terms of, even though this lower limit is constant, but upper limit is variable limit, and we are differentiating with respect to t. Therefore, I will have to use this particular law. So after application, what will happen over here? As I told you, this integration as it is 0 to t, differentiate this particular integrand function with respect to that corresponding variable. So corresponding variable is t, therefore derivative of v with respect to t. Okay. Then according to this particular law, what I need to do, I will have to replace, because integration is with respect to tau. Therefore substitute tau is equals to upper limit. Tau is equals to upper limit is t. Therefore I have substituted tau is equals to t, and derivative of t with respect to t is going to be a 1. Okay. Then minus term is there. I will have to put t is equal, now tau is equals to 0, but multiplicative term is derivative of 0 is 0, and therefore that term is not there. Okay, so this is the differentiation under integral sign of this particular integral equation, and of course, as per our condition, as per our prescribed problem, this particular value v of xt at t is equals to t is nothing but this initial temperature whatever we have prescribed, the f of xt, and therefore this equation number 73 will gives me derivative of the integral equation 72 with respect to time variable. Is that correct? Okay. Now I will go ahead, and one more derivative is required. Now I need the second order derivative of u with respect to x, because later on I will have to substitute in the governing differential equation. But now I need not to worry here, because limit is in terms of t. We are differentiating with respect to x. X and t are the independent variable. So directly I can differentiate under the integral sign. So uxx will gives me integration 0 to t vxx of that corresponding xt tends to tau and t tau. So that I can do directly. I need not to use that particular law. Okay, because these two are the independent variable, and now I will substitute this particular two values of derivative of u with respect to t and derivative double derivative, I mean second order derivative of u with respect to x in the governing differential equation. So governing differential equation, I will substitute. What will happen here? So the initial term I have substituted, the integral equation I just combine over here. Okay, I substituted value of ut. I have substituted a value of ut, I have substituted a value of uxx. Okay, so ut is there already, we have find out. Now this is here, and now what will happen, according to the parallel problem, what is the value of vt minus k vxx is 0. If you go back and if you see, this is the parallel problem. So parallel problem, vt minus vxx is 0. Okay, and its initial condition is f of x tau. So So this integrand term is 0, initial temperature is there, okay, and therefore I got only f of xt, and therefore governing differential equation is satisfied. What was the governing differential equation? Here it is. This is the governing differential equation. Ut minus kxs is equals to f of xt. So governing differential equation is satisfied. Now I will have to check the initial condition. The initial condition, when time is 0, u is 0. So initial condition is very much obvious, because what will happen here in this term, whenever I will put t is equals to 0, integration 0 to 0 is going to be a 0. Therefore obviously initial condition is also satisfied. So I have mentioned here. So thus this particular integrand solution satisfies the governing differential equation as well as initial condition, and therefore uxt will gives me a solution of the non-homogeneous problem. So this is the way that you can construct a parallel homogeneous problem, and you can add that internal heat source term as an initial condition, and then you can go ahead with our regular techniques of solving those homogeneous problems, okay, and then accordingly as an integral equation you will get the solution of non-homogeneous problem. So this is the way that you can tackle you can solve this particular problem. Okay, now as I told you, in the initial problem I have taken the 0 initial condition. First problem I have taken the 0 initial condition. Now if I replace the 0 initial condition by non-zero initial condition, then of course the corresponding problem again in the very similar fashion you can solve. Okay, in the very similar, only you will have to add the effect of this particular temperature function, non-zero initial temperature function, and the corresponding solution I have just mentioned here. If you are interested, you can solve this particular problem during your tutorial session somewhere. I think sessions are there. So this is very interesting problem. Either you can go very parallelly with the solution, way of solution just now I have shown. Otherwise, you can solve this particular problem with the help of integral transform technique. You can apply Fourier transform technique with respect to x. You can apply Laplace transform with respect to t. So both options are there. Only the choice of the integral transform, you need to be choose the correct corresponding variable. That is only the condition, but easily you can reach to this particular solution. Okay. One more important thing. This is now a boundary value problem. Earlier was the initial value problem. That is ut minus k a u xx is equals to f of xt. Okay, and this is a finite rod again. Okay, subjected to initial non-zero initial condition, that is f of x, and now the boundaries of the rod are subjected to 0 temperature. This is exactly same initial problem. Only the change is that, if you remember that this was the first problem explained by me. Only the change is that this is a non-homogeneous problem because of this internal heat source term. Everything is exactly same. Again, by the very similar fashion, what technique just now I have shown, you can find out the solution. Otherwise, again you have a choice of integral transform. Integral transform is a much better option for this type of problems, because this will you can easily reach to the particular solution. Of course, the solution will goes in the integral equation, that we don't have any choice, and that integral terms may be removed once we choose a particular value of fx. Once we select a particular value of fx, then this integral terms may be removed, and then we'll get simple mathematical expressions. So this is also another problem, which is a boundary value problem in a bounded domain. Okay, and the corresponding solution also I have mentioned. If you again you can try this another problem also. So all these are problems based on earlier what type of problem we have discussed in our earlier sessions, and even the technique just now I have shown for the non-homogeneous problem. So this is one thing, that non-homogeneous problem was not discussed in the earlier lecture, so I have added the techniques of solving non-homogeneous problem. Now here I will go to the uniqueness theorem, because you might be doubtful that what will happen with the uniqueness if we add this internal heat source term, because this extra term we discuss the homogeneous problem is existence, uniqueness and well-posedness. But what will happen with this particular term if we add this term, whether solution is unique or not? Of course, subjected to non-zero initial conditions, and boundaries are zero boundary condition. So theorem states that the solution of this particular problem in a bounded domain has a unique solution. So let us of course prove this. Proof is not that much difficult. Proof is very simple. Again let me explain. This is a non-homogeneous problem. Internal heat source term is there, non-zero initial temperature is there, and zero boundary conditions. Means at the boundary condition temperature prescribed is 0. So proof, of course, like our traditional uniqueness proof, I will consider suppose u1 of xt and u2 of xt are the two different solutions. Let us assume that, and I will consider v is equals to u1 minus u2. If u1 is solution, u2 is solution, v is also going to be a solution, and therefore v will satisfy the corresponding Mandro value problem, and therefore I will replace u by v over here. So this will satisfy the boundary condition, and of course this boundary condition will get changed, because v is nothing but u1 minus u2. So u1 initial temperature is f of x, u2 initial temperature is f of x, and therefore v will be fx minus fx, so zero initial condition. That I will have to take care of. Otherwise, this is the description of the boundary value problem. Okay, and now to show the uniqueness, what I will do, I will define one particular integral equation by E is 1 upon 2k integration 0 to L v square of xt. And obviously as per this particular definition, because L is some non-zero positive constant, v square is positive term, and therefore E is always more than or equals to 0 according to the definition of E itself. Now I will differentiate this E again with respect to t. So what will happen over here, if I differentiate, as limit is constant, so again I need not to worry about this limit is constant, so directly I can differentiate v as a function of t, and therefore this can be written as 2 times v, and derivative of v with respect to t will be vt. Of course I will get this particular equation. Okay, and now value of vt can be substituted as vxx, k times vxx according to the governing differential equation. Here it is, the value of vt is nothing but k times vxx. Okay, so I can take the advantage of that governing differential equation, and now I can solve this integral equation by using that integration by part. So integration by part, v will be as it is, integration of vxx will be vx, and integration of integrated term, that is vx, and of course the derivative of first term is vx nothing but vx square, I mean derivative of v with respect to x and its square. Now what will happen, what are the initial conditions? At when x equals to 0, v is 0, when x equals to L, v is 0, and therefore first term will vanish and second term is this way. As I told you, this integral equation is always positive as per its definition itself, and therefore this is less than or equals to 0. I mean to say that derivative of E with respect to t is negative always, and as it is negative, so I can conclude that E is a decreasing function according to our calculus law. Okay, so this is decreasing function, v of x0 is 0, and therefore ultimately E of 0 will be 0, and therefore ultimately what will happen, it's a decreasing function, E of 0 is 0, and therefore ultimately it is less than or equals to 0. But in fact what I can say here, according to, so it is never negative as per according to the definition, and therefore E of t is always 0, and whenever E of t is 0, therefore v must be equals to 0 according to this particular definition. Okay, so v is 0, and as v is 0, therefore of course the solution of the problem is unique. So this is a uniqueness theorem for the non-homogeneous problem of the heat conduction. Okay, now little bit as per our discussion in the last lecture. Okay, so and of course discussion with the few students, I have just added one problem of the Laplace transform technique, and before that a little bit I will talk about the integral transform technique, and this I have discussed, but here it is just a proper definition of the integral transform, and then I will go to the problem directly using the Laplace transform technique. So what we will do here, f of t is the of course a given function, then integral transform of f of t, it will be transformed to another variable, as I told you, suppose s, and this is transformed by the integral equation within the domain of that particular variable t. Suppose t varies from a to b, and kst, here kst is the kernel of that integral transform, and f of t is the original function. Okay, so this is the transformation of a particular function into the another domain is nothing but integral transform under integral sign via with the help of kernel. Now as I told you, These are the well-known transforms like Laplace transform, Fourier sine transform, Fourier cosine transform, Henkel transform, and this plays a very important role as far as this heat conduction problem is concerned. So kernel of the Laplace transform is e to the power minus st, is exponential kernel, and of course limit varies from 0 to infinity, and that's the reason this particular Laplace transform is applicable for the means transforming time variable because of this particular range, because t varies from 0 to infinity, time variable also varies from 0 to infinity, and kernel is also e to the power minus st, and you can better understand here as t tends to infinity, this value tends to 0, so that there is no any convergence, something like convergence issue or something. Fourier transform we discussed there, e to the power, this is in the form of course a complex, e to the power minus ist and upon root 2 pi. Root 2 pi is the normality constant. Whenever we are designing a particular kernel, then we will have to normalize it, because there should not be any effect of this particular kernel on the where that particular integral transform is being applied. Otherwise the magnitude of that corresponding function will get changed, but we don't want to do that. The magnitude needs to be the same whatever is under consideration, and therefore the kernel whatever you are considering, that must be a normalized kernel. So this is a normalized coefficient 1 upon root 2 pi or root 2 pi by something like. Of course range is minus infinity to plus infinity, and that's the reason whenever x varies from x is in the unbounded domain or in a real line, then this Fourier transform is most suitable transform. Fourier sine transform is also applicable in a half plane, like whenever x varies from 0 to infinity. Choice is also depends on the nature of the boundary condition, but that's a different theory. So I will not, otherwise again there may be a confusion, which even though variable varies from 0 to infinity in a half plane, that is a positive x-axis, that 0 to infinity. So which particular transform is applicable, when to use sine transform and when we can use a cosine transform, because range is the same, but that depends on the boundary condition, and that simplification and that theory goes to the Fourier transform of course, so I will not go there right now. And Henkel transform again for the R variable, the resulting solution is in terms of basis function, okay, and variable of course R varies from 0 to infinity. So this is little bit about the choice of the transform. If we look at the properties, here all space variables are created in the same manner as we discussed in the last problem, that is a application of the Fourier transform. Here del operator was with respect to, del operator was with the independent variable x, y, z, but as the second order derivative with respect to x, with respect to y, with respect to z, so all these three variables we have removed simultaneously with the help of Fourier transform. So it treats all the space variable having the same properties, okay, in the same manner. There is no inversion difficulty. Inversion difficulty, as I told you, once we apply integral transform on a particular boundary value problem, then to remove the effect of that particular integral transform, we will have to apply again inverse that corresponding integral transform. So inversion difficulty is not there except Laplace transform, because to take the inverse of the Laplace transform is little bit challenging, particularly in the application oriented problem. I will come to that problem later on. Otherwise in the last problem you have seen already that after application of the Fourier transform, we have just go back and we said the Fourier transform of f of x is suppose f of xi, then inverse of f of xi is f of x, and that integral equation and corresponding whatever is there, that mathematical complication was not there. But whenever you will apply integral transform of the type Laplace transform, then the inversion is little bit challenging thing. Okay, otherwise it's, and this integral transform is applicable for finite, semi-infinite, infinite regions. So all type of boundary conditions can be covered in the integral transform. And what is the most of the advantage? This is the most beautiful advantage, that is it converts the partial differential equation into ordinary differential equation. And once we come to the reach into the form of ordinary differential equation, it's easy to solve, as we are aware of that, and then we will reach to the particular solution. Only the drawback what I have seen you might have observed in the last application also that the solution of even the problem is in the bounded domain, the solution is in terms of infinite series. If solution is in terms of infinite series, then again you will have to check the convergence and all those things. That will come into the picture, that you will have to check the convergence of the infinite series. But that also you can do very easily because the computing facilities are available, so many softwares are also available. So you can usually check the convergence of that particularly infinite series. Okay. So I will come to the application of Laplace transform directly. So here f of t is the function defined on t positive. Okay, then its Laplace transform parameter is suppose p. So f of p will represent the Laplace transformation of f of t, and its integral 0 to infinity a to the power minus pt is the kernel of Laplace transform f of t dt. Okay, and only two properties only I have added which is required for my solution of the problem. So here I will denote the Laplace transformation of f of t by capital F of p. P is the parameter. And how can we find the Laplace transform of nth order derivative? So Laplace transform of nth order derivative formula is like this: p to the power n f of p. F of p means Laplace of ft. P to the power n minus 1 f0, value of the original function at t equals to 0. P to the power n minus 2 f dash 0. P to the power n minus t f double dash 0, and up to the it's all successive derivatives. Okay. As far as this particular partial differential equation is concerned, as I am going to apply Laplace transform with respect to time variable, therefore here u, temperature u is function of x and t. Now x will be carried forward as it is. In the last problem when we applied the Fourier transform, we were carry forwarding as it is t variable, and all those treatment was for x variable. Now here x will be as it is and t will be converted in terms of Laplace transform parameter, that is p, and I will denote Laplace transform u by u bar. Okay, so if it is with respect you are taking Laplace transformation of derivative of u with respect to x, simply you can write derivative of u bar with respect to x. It will not. Similarly in the second order derivative, multiple derivatives here, of course here if we use this particular formula, then Laplace transformation of derivative of u with respect to t, this is the first order derivative. Therefore according to this particular formula, n is equals to 1, and therefore how can we write? P is equals p to the power of 1. Laplace of the given function is u, Laplace of the function is u bar x p, and of course derivative value of the u at x t equals to 0. Okay, so this is the way that we can apply the Laplace transform on the differential terms. Second order derivative, how can we write? P square, Laplace of u is u bar, then p, value of u at t equals to 0 minus p to the power 0, that is 1, and derivative of u with respect to t at t equals to 0 according to this particular formula. Okay, so this is only needed over here. Okay, so I will come directly to the problem and we'll just see, because we are learning the various techniques of solving the heat conduction problem. So I thought we should not miss this technique also. This is also a very useful technique, of course. So here I will consider a bar of length L. Again, this is a bar of length L. Okay, at the constant temperature U naught. Initially, whenever t equals to 0, the temperature is 0. X equals to L is suddenly given the temperature U1. Okay, at the end x equals to 0, that is the insulated. Okay, and assuming these conditions, find the temperature. Now you need to formulate first of all the problem. What type of description given in the problem? So firstly you need to understand this is a rod, metallic rod of length L. As we are discussing its heat conduction, so here you can see this one-dimensional heat conduction problem is applicable over here. This coefficient is written in the different fashion. You need not worry about this particular coefficient. This is normally thermal diffusivity that I told you. Okay, so this is one-dimensional heat conduction problem. X varies from 0 to L and T is more than or equals to 0. What is the second boundary condition? The initial temperature of the rod is U naught and T is equals to 0, U is equals to U naught. So initial temperature means here U is function of X and T. So whenever T is 0, U is U naught. For all X varies from 0 to L. Now second thing is that the X equals to 0 end is insulated. I told you the mathematical meaning of the insulation. Insulation means there is no heat exchange. This is x equals to 0, this is x equals to L. This end is insulated means there is no heat exchange within the surrounding area. And therefore, the rate of change of temperature is 0 at that particular end. And therefore, Ux at x equals to 0 is 0. Whereas, the second end is subjected to non-zero temperature, that is x equals to L, U is equals to U1. X equals to L, U is equals to U1. So this is the mathematical formulation of the problem. Equation 1, 2, 3, 4 represent the mathematical formulation of the problem. Here I am going to apply Laplace transform. So this is the flow chart of the problem, solution of the problem. The governing differential equation, here U is the dependent variable, X and T are the independent variable. In order to solve this particular problem, I will apply Laplace transform with respect to time variable. And of course, time variable is, the Laplace is applicable for time variable that I told you. After applying Laplace transform, this partial differential equation will convert into ordinary differential equation with single independent variable x. So this is ordinary differential equation. As per our regular techniques of solving ordinary differential equation, I will find its solution, and then on this particular solution, because this solution will be in the Laplace transform domain. So I will have to remove that Laplace transform domain. Therefore, for that purpose, I will have to apply the inverse Laplace transform technique, and of course, applying inverse Laplace transform, I will get a final solution. Only the thing is that unlike a Fourier transform, this inversion will have to do a lot of mathematical activities. That is only the, what you can say, maybe disadvantage of this particular transform. So let us go step by step. Firstly, I will apply Laplace transform on both sides of the equation. Operator L is nothing but Laplace transform. Now, as I told you, the Laplace transform is applicable with respect to time variable, and therefore here I will have to use that rule, the Laplace transform of derivative. So Laplace transform of derivative, order is 1. Order is 1, therefore p to the power 1. Derivative of u is taken, therefore Laplace transformation of u is u bar x, and t will be converted in terms of Laplace transform parameter, that is t, and first order derivative, so p to the power 1, after that immediately p to the power 0, and this particular function at t equals to 0, that is ux0. And here c square is of course constant, that I can carry forward as it is, and as we are taking Laplace transform with respect to t, therefore this term directly I can shift it to the derivative, double derivative of u bar. U bar represents the Laplace transformation of u. Now this value is already known to us, ux0, that is the initial condition. Initial condition is u0, so I can substitute this value u0 over here. So I got the corresponding ordinary differential equation. I have just rewritten this particular differential equation, that is the second order derivative of u bar with respect to x minus p by c square. P is the Laplace transform parameter. U bar is equals to this constant initial temperature. I have shifted to that particular side, u0 upon c square. So this is after application of the Laplace transform, we have converted this partial differential equation in terms of ordinary differential equation. And now we know how to solve this particular ordinary differential equation. We'll have to find its complementary function and particular integral, and that techniques are very much familiar to us. So this I have used the operator of d. D operator is derivative with respect to x. Its corresponding roots can be written like this, and this can be written either in the exponential function, or we can write in the hyperbolic function. That theory part already you known to us, and therefore the complementary function of u can be written as a cos. I have written in the hyperbolic function, so the cos hyperbolic, okay. So p square by root of p by c square x, and b sin hyperbolic, that particular term. To find the particular integral, I will have to shift this operator that particular side. So inversely operated this particular operator, as this is a constant. So according to our regular technique, I will have to substitute d is equals to 0, operator d goes to 0, and therefore corresponding particular integral I got, okay, and just sum of the complementary function and particular integral will give me solution for u bar. So I obtained the solution for u bar, but here u bar is function of variable x. X is our original space variable, but the t is not there. T is in the transform form, that is p, and that is only the thing that I will have to I obtain this particular solution in the Laplace transform domain, and then I will have to shift it to the original variable t. Now here I will have to first of all find this unknown constant a and b, and then I will go to the inversion of the Laplace transform. So to find the a and b, I will use two boundary conditions. I have two boundary conditions. One is derivative of u with respect to x at x equals to 0 is 0. So whenever I am using the boundary condition, directly I cannot use it. I will have to, again, as I have applied Laplace transform on the original governing differential equation, I will have to apply Laplace transform on the corresponding boundary condition also. All this problem I will to shift in the Laplace transform domain. So that care I need to take, and therefore before applying this particular boundary condition, I will apply Laplace transform over here. Okay, so on applying Laplace transform, now here derivative of u bar with respect to x at x equals to 0, and then I will take derivative of that earlier solution, and then I will put x equals to 0. If I put x equals to 0, sin hyperbolic 0 is 0, and therefore in order to have the 0 solution, I must have b is equals to 0. This is very simple thing, nothing new over here. Okay, so b equals to 0, I will resubstitute in the last solution, so b term vanishes and remaining term is this. Now I will find out constant coefficient a. For that I have another boundary condition. Whenever x is equals to L, u is equals to u1. Again, as I told you, I cannot use directly this boundary condition. I will have to apply Laplace transform, and then I can go for application. So I will apply Laplace transform, that is Laplace transform of u is nothing but u bar, and Laplace transformation of u1. u1 is a constant initial temperature, and therefore u1 I can take outside if I solve this integral equation. Otherwise you can see u1 coefficient is 1. So Laplace transformation of 1 is 1 upon p. If you don't know, you can solve this integral equation, you will get it. So what I got is shifted, transform initial, boundary condition, not initial, boundary condition. Whenever x is equals to L, u bar is equals to u1 upon p. So I will put u bar is equals to u1 upon p, x is equals to L, and I can rewrite this particular equation. I will get value of a. So I got a as a coefficient. I will substitute in the last solution, and this is the solution of the given boundary value problem in the Laplace domain. But as I told you, this particular solution is in the Laplace domain. Here variable of u, u bar is the function of x and p. P is not required, P is not our desired solution. So I will have to shift, I will have to go back, and I will have to transform P to T, and for that purpose I will have to take inverse Laplace transform. So this is the mathematical work now we need to do. I will have to apply Laplace transform, and I will have to find the inverse Laplace transform of this particular equation. So this is here the additional steps are required. So next step is use of inverse Laplace transform. Now to find the inverse Laplace transform, I will apply L inverse operator. So L inverse operator, u1 minus u0 is constant, I can take it outside. Inverse operator on the first term as well as second term. The second term is easy, because as I tell you, Laplace transformation of 1 is 1 upon p. So inverse Laplace of 1 upon p is 1, and therefore this directly I can write. But this term is a little bit complicated term, so we will have to do a mathematical treatment for this particular term, of course, here L. Okay, so this term is there. So how to find the L inverse, inverse Laplace of this particular expression? So for that I will have to use complex inversion formula. And what is that complex inversion formula? This complex inversion formula, this constant coefficient I have just carry forward everywhere, u1 minus u0. Complex inversion formula tells us 1 upon 2 pi I integration gamma minus I infinity to gamma plus I infinity. This particular expression as it is, okay, e to the power pt is the kernel of that integral, and integration is of course with respect to parameter p. So this is complex inversion. This term is also I will carry forward as it is. So I will have to solve this particular complex inversions, and that can be done by finding our again regular techniques of the complex analysis, that is by finding the poles and residues. We will calculate poles and residues, and accordingly I will get value of the integration. Okay, so that mathematical treatment is essentially required over here. So value of this particular integral is nothing but the sum of the residues of this particular expression at their poles. So to find the pole, again you can see here the denominator is this particular expression, so p equals to 0, okay, and cos hyperbolic square root of p upon c square into L is equals to 0. So p equals to 0 is the one pole, and this second thing is cos hyperbolic theta is equals to 0 when theta is multiple of pi I, I mean n minus half multiple of pi I, and therefore this particular theta, this particular angle is nothing but n minus half pi I. Of course n can take any positive value, negative value, and 0. So by solving this particular expression, I will get p equals to 0 is of course a simple pole is there, and the another pole, I mean this is a multiple poles, okay, so this can be written as minus 2n minus 1 square pi square c square upon 4a square. I will call it, for the simplicity I will call it as a pn, because that depends on n. N is integer. So find the residue. Again, our day-to-day technique is applicable, that p tends, I will have to take limit p tends to 0, p minus 0 into that particular expression. Of course, and on solving this, I will get value 1. Okay. Now p is equals to pn, again residue at the p is equals to pn. I will apply the same formula, that limit p tends to pn, p minus pn upon this. Now again, to solve this particular limit, what I will do, I will just rewrite these terms like this. I will collect the term p minus pn upon this cos hyperbolic term, okay, and into another bracket I will write e to the power pt cos hyperbolic term upon p. Because after writing the expression in this particular form, what will happen here, the first bracket is in 0 by 0 form, because limit we are taking as p tends to pn, and here p is equals to pn is the pole of this particular expression. So obviously this is going to be a 0, and therefore this first bracket is in 0 by 0 form. Second bracket directly I can put p is equals to pn, it will not make any singularity. So 0 by 0 form, therefore again by applying that L'Hospital rule, differentiate numerator and denominator and all those things. So differentiating, and then after substituting, and then after simplification, a lot of mathematical work is required there, of course, okay, and then I will get this particular expression. So residue is calculated over here in this particular, from after doing a lot of mathematical calculations and all those things. So I have substituted p is equals to pn and all those things. So this is the expression, and this expression you can observe here the cos hyperbolic, and angle is again in the form of pi I. Here sin hyperbolic angle is again in the form of pi I. So that we may remove by our regular properties of the hyperbolic function, okay. So that can be done here by using this particular, that's cos hyperbolic of ix is cos x, and sin hyperbolic of ix is I times sin x. So again, those all mathematical fundamental mathematics is required, and then accordingly I will get the corresponding residue. And once I get the residue, the sum of the two residues, earlier one we have already calculated, this is second, if we add it, so this will give me a final solution over here, okay. Again final solution, I have just converted this hyperbolic function into the circular function, and the corresponding solution is this. And then after that again I can combine, because this is valid for all n, so I can combine it, I can just sum up all the solutions. So this is the desired temperature within that particular rod, and this will give me the solution of the boundary value problem. So important thing is that whenever you are applying the Laplace transform technique, okay, so you can apply the Laplace transform technique with respect to time variable, but while inverting the Laplace transform, again you have to do some special techniques. Our regular, only directly you will not get some standard function, the Laplace transform of this particular function is this, therefore inverse, this is not going to happen. So here the complex inversion technique is the most useful techniques. It works, okay, in the real life problem also. So this is the way that we can apply Laplace transform and we can find out the solution. I don't know how much time is there. Otherwise I think a little bit I will just I will take 2 or 3 minutes only. So I tried to cover within my 4 lectures, I tried to cover the various techniques of solving the boundary value problem in the heat conduction area, bounded, unbounded domain, homogeneous, non-homogeneous, okay, isotropic only that we have restricted. Okay. One important thing, one interesting thing before concluding my session, I will just tell you. You might have heard about the fractional calculus is a very hot topic in day-to-day mathematics, and people are using as a wide scope of application over here. So I will just talk little bit, 2 minutes only. So actually what happened when this calculus theory developed, maybe in the 17th century or something, like before that even 16th century, okay, and all those mathematicians were working in the various calculus based properties of the differentiation, integration, limit, continuity and all those things. That time, okay, when this calculus and particularly differentiation developed, and differentiation, after developing differentiation, then again first order derivative, second order derivative, nth order derivative, this comes into picture later on. So this is very interesting historical notes just I want to share with you people being a mathematician. A particular date is available in the literature, September 30th September 1695. This particular date is available in the literature itself. Yale Hospital raised a question to the Leibniz: what will happen whenever you are talking about the successive derivatives, first order, second order, third order, integer order derivative, what will happen when n is not integer? He meant to say what will happen when n is real. Ahead of that, more generalized, you can say what will happen when n is complex. So that question was raised by Yale Hospital to Leibniz. He wrote a letter to the Leibniz and he asked what will happen. Of course, Leibniz was unable to answer that particular question that time, and he said it's an apparent paradox because we will not I don't have any particular mathematical answer for that. But later on, of course, this question, what will happen, of course, this is nth order derivative and this theory, Leibniz, you know, when Leibniz worked on that. So Yale Hospital asked him what will happen when n is equals to half. Okay. So later on, many scientists work on that, like Euler, Laplace, Fourier, Lekerox, Abel, and so many things. So then these people, these mathematicians, and after their next mathematicians started to work on that, and the first problem solved by Lekerox in 1819. In the 1819, this first problem on the fractional derivative started. So later on, of course, the people started to work on that. So this is a big history. So this is that particular problem. I will just keep it over here. And again 1832, that Riemann Levelly given, even though he solved the particular problem of the fractional derivative, but he could not give a generalized definition of the fractional derivative. So generalized definition of the fractional derivative given by this Riemann and Levelly in the 1832, and then he designed first of all a fractional integral, and on the basis of that fractional integral he came to that Riemann-Levelly fractional derivative. Okay. So and later on, recently in 1967, Capito defined a fractional order derivative with respect to time variable. So and recently, within 10-15 years, maybe 15 at the most 20 years, so this fractional calculus has a wide scope of application in the real life problems. People are using, even I am using our analysis work, we are not using the simple derivatives, but we are using it as a fractional derivatives, because the reason is very simple or very clear over here. The fractional derivatives is a non-local operator. Normally, whenever we are talking about the derivatives and the neighborhood is under consideration and limiting things, we are talking about that mathematics is well known to you people. But whenever we are talking about the fractional derivative, it's a non-local operator, and therefore calculating time fractional derivative of a function at a particular point t is equals to t1, it requires all past history. So that's the reason it's a memory. It considers the memory based effects, and now you can better understand in the physical sense. If a particular operator, if it considers the past history, it works as a memory base. So how this is applicable in the real life field? That's the beauty of this particular operator, and that's the reason many scientists, many mathematicians gives a better choice rather than using, particularly with respect to time variable, because time variable with means in the context of fractional derivative has a wide scope of application in the various fields. In the digital signal process, as I told you, in the designing of the materials and structures. So this is a very useful operator, and this is a very attraction, means topic of attraction as far as application area is concerned. So people have started to use, not only started, means this recent development within last 15 years, you will find a lot of research paper on this particular area. Here we have also worked not only simple heat conduction equation, but the heat conduction equation in the context of fractional derivative. So this is the beauty of what you can say the fractional differential operator. Okay, and of course this will give the many idea about the, once you consider a particular heat conduction problem, then and if you analyze it, if you find out the solution and all those things, then this will give the better idea about the dimensions, geometry, physical property, composition of the material. Like as I told you, the earlier problem from which we started here, so abnormal behavior of the physical system, all those things we can do mathematically by constructing the mathematical model of that particular problem. Of course, then we can find out the mathematical solution, and with the help of those mathematical solutions, we can predict a lot about that particular physical system. And this will work as an input for the further experimental things. And that's the reason what I started in my first lecture, that we as a mathematician can contribute a lot of things over here, because we don't need anything. We need just a plain paper and pen, and that's all. So our investment, that's why I have written here, it's a big economically beneficial. Otherwise one has to do, engineers and all those has to do a lot of experimental setup. But before their experimental setup, if one goes through the mathematical analysis, if we find out its characters, if we find out its physical characters, if we find out what is the required dimension for that, how much dimension is capable to bear the particular heat transfer happening in that particular system, then this will help as a guideline, this will help as an input for their further experimentation. And I am not talking hypothetically, we have done this already. We have done a collaborative work with many engineering peoples, okay, and I have given them, as a mathematician, I said, let me just do my I used to call it as a mathematical experiment. So let me do a mathematical experiment. I will give you inputs and you just check it whether those inputs really work practically or not. And competently I can say here over here, yes, it works really practically. So that's the beauty of our mathematician. So we are not only like working in classroom teaching or something like a hypothetical problems, but we can contribute very much in the real life problem in that sense. So I think I will conclude over here. Okay. So these are the references what I use during my lectures. Partial differential equation, this is a well-known book of Fritz John. Then Poland book is there, partial differential equation. Little bit what I talk about the Fourier series and related, that good kernel properties. This is a Santacruz, very good book for that. Okay. Snedon is a well-known book for the integral transform, and T. Amarnath is also a good book as an elementary partial differential equation. So these are the references I have included. So thank you. If you have any question, you please do not hesitate to talk with me. Okay. Any question? Yes, please.
In heat transfer,
Yes.
that problem you solved, at the end we get answer. So there are infinite terms in it. So in real life scenario, how do you calculate approximate solution?
Approximate solution, as I told you in the earlier lecture, that only approximate solutions one has to go only if closed form solution is not applicable, means not available. Then you can go for approximate solutions with the help of what you can say finite difference method, or what you can say finite element method, finite volume method. So those techniques you can use for your approximate solutions. But as far as this particular problems are concerned, as we are working in the multi-dimensional problems, or what we can say in the of course three-dimensional geometry, and we are using again a fractional derivative. So we are finding a semi-analytical solution. Semi-analytical solutions means everything we are doing with the help of integral transform, and finally only up to the we are achieving solution in Laplace domain, up to Laplace domain. But after reaching Laplace domain, as I shown you right now, it's very challenging to find out the inverse Laplace transform, and particularly in the context of fractional derivative. If one has used that fractional derivative with respect to t, so this type of terms are there. It is derivative of u, okay, with respect to alpha. Alpha is fractional, okay. So to invert this type of derivatives are there, okay. So alpha is fractional order. So after applying Laplace transform to fractional order, there are certain rules. That theory is also developed, okay. But after applying Laplace transform, its inversion is very challenging. And as of now, we are not able to find the inversion in the analytical form. So that time we are using some numerical techniques for finding inversion. So we used to call it as a semi-analytical solution. Means we are applying the integral transform technique to original problem, and we are achieving solution up to Laplace domain. And after, once we got the solution in the Laplace domain, analytical solution, then inversion is done in the numerical form. Okay. Any other question? So, thank you.